Hello and welcome. We are from Avektive. This time around, we'd like to present you our approach of designing energy demand forecasting model with a lead time of 5 hours. Here we go. To begin with, we have this methodology to follow. Firstly, we examine the data and its statistics. Secondly, we normalize the data and set our baseline risk. Thirdly, we fit the training and test set on risk function. Next, we improve the performance, and finally, we check our best model for reproducibility. Using Python with pandas and matplotlib, we can easily see the number of samples and view the raw data graph. As expected, the data oscillates with significant spikes in demand of power every summer and winter. The cycle, driven by season, is as if it's annually regular. Adding statistics and persistence loss function in prep.m, we can extract our data statistics. Here, the persistence loss is our baseline to beat. Using median and range values, we can normalize the data with this formula. You can see the change of data before and after being normalized. Again, the baseline risk is our persistence loss. Now, the exciting part begins. Using a difference network architecture, we fit the training and test set on risk function by tuning several hyperparameters as shown below. The difference network helps us achieve better learning. It's good to start experiment with simple design. Thus, we use naive window with 2 layers, 6 inputs, and various NN sizes to compare the item and SGD performances. Here, our first test loss has beaten the baseline risk. But wait a minute. Although item is better than SGD in terms of the performance, the scatter plots are not that linear and the design has no zero lag. Hence, to reduce the lag, we can change the input features from naive to diff. With the same model as before, we modified the input features using diff setup with 19 inputs. Here, we produce a better test loss than before. As you can see, scatter plots are seen better in forming a straight line than in experiment 1. Besides, we could achieve the zero lag while still minimizing the loss. But is it enough though? Nope, we can still do more. In the next step, we can improve the model performance by minimizing the risk while maintaining zero lag. The tools are making the network bigger or deeper, some changes in features, adding dropout layer, plus regularization. In this third experiment, we add more layers and perceptrons to the network and introduce dropout layer. We run multiple configurations and the results are shown here. The best configuration in this experiment are the network with dropout probe 0.05 and N size 128 and with Adam solver. We managed to minimize the risk while maintaining zero lag. Next, we will try to add L2 regularization and see what happens. In the fourth experiment, we combine the dropout layer with L2 regularization while keeping the previous settings unchanged. We run multiple configurations again, and the results are shown here. Turns out, the test loss is slightly increased, and the other results seem not to change that much. Furthermore, for 2 consecutive experiments, the best hyperparameter settings remain unchanged. Therefore, we can pick these values to design our final model. In this final experiment, we fit the best hyperparameter settings to the network except the regularization. We run 10 repeats to find the variability and to make sure that this is a correct conclusion. As you can see, the test loss is smaller than the training loss. The loss starts to converge from 350 iterations. Since data is visually somewhat periodic and predictable, the test samples can be contained in the training set. As a result, if the model has been trained well, then the training error can possibly be greater than the test error. We achieved the best test loss using this final model, which is stated on the table. While having no lag, the scatter plots of actual versus training test predictions form a straight line, means that our predictions are pretty accurate. In summary, we have our test error smaller than training error. In the difference network, Adam Optimizer outperforms SGD in terms of producing good results. When it comes to historical data, the diff window gives a better solution to minimize the risk and reduce the lag. Bigger and deeper network helps the model memorize well, but always be careful of overfitting. Dropout layer with small dropout probability helps the network improve the performance. And finally, be more considerate of using regularization. We really appreciate for your time to watch our video. In the end, stay humble, stay hungry, and stay motivated everyone. Thank you. Bye for now.